What If? Serious Scientific Answers to Absurd Hypothetical Questions by Randall Munroe. Picture this. You're at a baseball game, hot dog in hand, when suddenly the pitcher winds up and releases a fastball traveling at 90% the speed of light. What happens next? Well, let's just say you won't be catching it on your phone camera. You'll get nuclear fusion, a rapidly expanding bubble of plasma, and a mushroom cloud that erases the city from existence. Home run? Not quite. More like ground zero. Welcome to the wonderfully weird world of What If, where the most ridiculous questions you can dream up get answered with dead serious science. It's a playground where curiosity isn't just allowed, it's the whole point of being there. The genius orchestrating this beautiful chaos is Randall Munroe. Here's the thing about Munroe that makes him perfect for this job. Before he became internet famous for his stick figure webcomic XKCD, he was actually building robots at NASA. Yeah, actual NASA. The guy literally worked on machines designed to explore other planets. Then one day, he decided to quit and draw comics instead. But he brought all that scientific firepower with him, and now he uses it to answer questions like, what if everyone on Earth jumped at the same time, from people on the internet who probably should be working instead? What If turned into a massive hit, selling millions of copies and proving something important. Science doesn't have to be boring lectures and memorized equations. It can be a rocket ship for your imagination, a way to explore the wildest corners of possibility. It reminds us of that pure childhood joy we felt when we'd ask why about everything, before we got too grown up and serious to wonder anymore. Today, we're diving headfirst into that world. We're going to push physics to its breaking point, poke holes in reality, and see what happens. And here's my promise. By the time we're done, you'll not only know the answers to questions you never knew you had, but you'll also remember what it feels like to look at the universe and think, what if? Let's kick things off with a question that sounds innocent, but is actually apocalyptic. A reader named Andrew Brown asked, what would happen if the Earth and everything on it suddenly stopped spinning, but the atmosphere kept going at full speed? Short answer, total pandemonium. But the details? Oh, the details are where it gets fascinating. Right now, as you're listening to this, you're spinning. The Earth's surface at the equator is whipping around at over 1,000 miles per hour, about 470 meters per second. If the ground suddenly slammed on the brakes but the air didn't get the memo, you'd have an instant worldwide wind of absolutely biblical proportions. For about 85% of humanity living between 42 degrees north and south latitude, that wind would be supersonic. Think about that. A wind moving faster than sound itself. For a few insane minutes, this tornado on steroids would sandblast the entire surface of the planet. Sure, friction would eventually slow it down, but not before it turned virtually every human structure into kindling. Skyscrapers, houses, the Golden Gate Bridge, all of it would get ripped from the ground and turned into high-speed projectiles. Even places far from the equator, like Helsinki, would experience winds stronger than the worst tornadoes ever recorded. Nobody's safe. And it's not just the wind you need to worry about. It's what the wind is carrying. Even if you're hiding in a nuclear bunker, your neighbor's house just became a 1,000-mile-per-hour missile with your name on it. Your odds of survival? Pretty much zero unless you're deep underground when it happens. Maybe in a subway tunnel or a basement. Oh, and the scientists at the South Pole Research Station would probably make it. For them, the first clue that something's gone horribly wrong would be silence. Every communication channel on Earth suddenly goes dead. Then, someone would glance outside and notice something really strange. The sun has stopped moving across the sky. As the surface winds finally die down, things somehow get even weirder. All that kinetic energy from the wind transforms into heat, scorching the land and triggering massive thunderstorms wherever there's moisture. The wind racing over the oceans would whip the surface into such chaos you couldn't tell where the water ended and the air began. The churning would drag freezing cold water up from the ocean depths, creating bizarre new weather patterns, swirling mixtures of wind, fog, and wild temperature swings. Oh, and there'd be a storm surge, the biggest in history. A wall of water would sweep around the globe like a slow-motion tsunami, pushing miles inland. With the Earth no longer spinning, day and night as we know them would end. Each day would last 6 months. One side of the planet would roast under constant sunlight, while the other side plunged into an endless, frozen night. Sounds pretty final, right? But here's where it gets oddly hopeful. We'd have one silent guardian slowly working to fix things: the moon. See, right now the Earth spins faster than the moon orbits us, and the moon's tidal forces are actually slowing our rotation down, very, very gradually, while pushing the moon farther away. But if we stopped spinning, the whole dynamic would flip. The moon's gravity would start pulling on our stationary planet, working like a cosmic motor to get us spinning again. Slowly, over an unimaginably long time, the moon would actually undo the catastrophe and get the Earth turning once more. Pretty terrifying to imagine our whole planet subjected to that kind of disaster. But what happens when you take that same level of cosmic energy and shrink it down to something much smaller? What if the disaster isn't planetary, but happens on a single baseball diamond? This brings us to one of Munroe's most famous answers. What would happen if you tried to hit a baseball pitched at 90% the speed of light? Picture a normal game. Normal pitcher, normal batter. But the instant the ball leaves the pitcher's hand, it magically accelerates to 0.9 c. That's over 600 million miles per hour. From that moment on, normal physics takes over. The ball is moving so insanely fast that everything else, including the air molecules in front of it, might as well be standing still. Normal aerodynamics don't apply here. The air doesn't have time to flow around the ball. Instead, the ball collides with air molecules so violently that the atoms in the air literally fuse with atoms on the ball's surface. Each tiny collision releases gamma rays and scattered particles. These spread outward from the pitcher's mound in an expanding bubble, ripping electrons from atoms and turning the air in the stadium into a growing sphere of glowing plasma. This wall of nuclear fire and radiation races toward the batter at nearly the speed of light, arriving just fractions of a second before the ball itself. The constant fusion reactions at the front of the ball work like a rocket engine in reverse, pushing back and slowing it down. But the ball is moving so ridiculously fast that even ongoing thermonuclear explosions barely make a dent. They do start eating away at the ball's surface, though, blasting off tiny fragments that trigger their own fusion reactions when they hit more air molecules. About 70 nanoseconds later, what's left of the ball reaches home plate. The batter hasn't even seen the pitcher release it yet. The light carrying that image arrives at basically the same time. The ball isn't even a ball anymore. It's a bullet-shaped cloud of expanding plasma, mostly carbon, oxygen, and hydrogen, still triggering fusion reactions as it travels. The shell of X-rays hits the batter first. A few nanoseconds later, the cloud of plasma arrives. It slams into the bat, the batter, the catcher, and home plate, scooping them all up and carrying them backward through the backstop as they completely disintegrate. In the first microsecond, the bubble of superheated plasma swallows the backstop, both teams, the stands, and the entire neighborhood around the stadium. If you were watching from a safe distance, say a hilltop outside the city, you'd first see a blinding flash of light, brighter than the sun. This would fade over a few seconds and be replaced by a growing fireball rising into a mushroom cloud. Then, with a deafening roar, the shockwave would arrive, uprooting trees and shredding buildings. Everything within a mile of the park would be flattened. The baseball diamond? Gone. In its place, a sizable crater. And the batter? Well, according to Major League Baseball Rule 6.08b, the batter would be considered hit by pitch and would be eligible to advance to first base. So whether we're talking planetary catastrophes or microscopic mayhem, unleashing that much energy rarely ends well. But not all extreme scenarios are about destruction. Some are just profoundly weird. Take this question from reader Sean Rice. What would happen if you gathered a mole, the unit of measurement of moles, the small furry critters, in one place? First, let's talk about what a mole actually is. It's not like a pound or a meter. It's just a number like a dozen or a billion. Except it's a stupidly big number. 602, 214, 129 quadrillion. It's so huge we only use it to count things like atoms and molecules. So what would a mole of actual moles, the burrowing mammals, look like? Let's do some quick math. A mole is small enough to hold. So let's say it weighs about 75 grams. Multiply that by the number of moles in a mole, and you get a total mass of about 4.52 times 10 to the 22nd kilograms. That might not mean much to you, but it's a little over half the mass of our moon. We're talking about a planet-sized pile of moles. If you gathered them all in space, their own gravity would pull them into a sphere. You'd have a new planet in our solar system, Planet Mole, a meat planet. It would be slightly bigger than the moon, with surface gravity about 1/16 of Earth's. And here's where things get properly disgusting. The immense pressure in the planet's core, over 100 megapascals, would be high enough to instantly kill any bacteria, sterilizing the mole remains. So most of the planet wouldn't decompose normally, but near the surface, where pressure is lower, anaerobic bacteria, the kind that don't need oxygen, would start breaking down the mole tissue, releasing tremendous amounts of heat. This would heat the planet, but only to a point. As the temperature rose, the bacteria would die off. The outer surface would radiate heat into space and freeze, forming an actual fur coat that would insulate the liquid interior. Plumes of hot meat and trapped gases like methane would periodically erupt through the crust in what can only be described as geysers of death, blasting mole bodies out into space. Eventually, after thousands of years, the planet would cool and freeze solid. The water in the mole bodies would crystallize under the immense pressure into exotic forms of ice, like Ice 5 and Ice 9. It's bleak and bizarre, but Munroe points out something weirdly optimistic. There might be 1 billion habitable planets in our galaxy. If we colonized even a fraction of them, and brought small mammals along, then over a few million years, the total number of moles that will have ever lived would easily surpass Avogadro's number. So if you really want a mole of moles, you don't need magic, you just need to build a spaceship and be very, very patient. From the cosmic to the biological, the questions in this book span every imaginable scale. But some of the most fascinating ones deal with us, with humanity, our society, and our limitations. What happens when you gather not a mole of moles, but all of humanity in one place? Reader Thomas Bennett, along with many others, asked, what would happen if everyone on Earth stood as close together as possible and jumped, everyone landing on the ground at the same instant. First, the jump itself. The entire population of Earth, crowded together, would take up an area roughly the size of Rhode Island. At noon, everyone jumps. Does it affect the planet? Not even slightly. Earth outweighs us by a factor of over 10 trillion. The push from our jump would move the planet by less than the width of a single atom. So the jump itself is a total dud. Everyone lands. The sound of billions of feet hitting the ground creates a long, drawn-out roar. But that's it. The real story begins after the silence returns. Everyone is in Rhode Island, all 7 billion of us, and nobody knows how to get home. First thing that happens? Every cell phone network on the planet collapses. Billions of phones, all in one spot, all searching for a signal. The system would be overwhelmed instantly. Outside Rhode Island, the world, now empty of people, grinds to a halt. Power plants fail, machinery stops, and an eerie silence descends on our abandoned cities. Back in Rhode Island, chaos erupts. The airports, even running at maximum capacity, couldn't put a dent in the crowd for years. The highways would become the site of the largest traffic jam in human history as people grabbed cars, only to run out of gas a few miles later. The crowd would start spreading outward into southern Massachusetts and Connecticut. But there's a problem. Almost nobody speaks the same language, and almost nobody knows the area. Society breaks down. Violence becomes common. Everyone's hungry and thirsty. Grocery stores get emptied in hours. Fresh water becomes the most precious resource, but with no distribution system, it's nearly impossible to find. Within weeks, Rhode Island becomes a graveyard of billions. The few survivors spread out across the empty continents, struggling to rebuild civilization from the pristine ruins of the old one. Our species survives, but it's a shadow of what it was. Earth's orbit, of course, remains completely unaffected. It spins on just as it always has. But at least we'd finally know what happens if everybody jumped. From the fate of humanity to the fate of a relationship. What if the connections we feel weren't about choice and chemistry, but were actually written in the stars? Reader Benjamin Staffen asked, what if everyone actually had only one soulmate, a random person somewhere in the world? What an absolute nightmare that would be. First, let's set the rules. Your soulmate is a real person, chosen at random. You don't know who they are, but you'll recognize them instantly when your eyes meet. The first problem is grim. 100 billion humans have ever lived, but only about 7 billion are alive today. If your soulmate was chosen from everyone who ever existed, there's a 90% chance they're already dead. And if we include people from the future, your soulmate could be someone who won't be born for another 1,000 years. Let's make it easier. Your soulmate is alive at the same time as you and close to your age. That gives you a pool of about 500 million potential matches. The odds are still crushingly against you. Think about how many new people you make eye contact with each day, maybe a few dozen if you're outgoing. Over a lifetime, that might add up to 50,000 people. Given a pool of 500 million potential soulmates, you'd find your true love in only one lifetime out of 10,000. The vast majority of us would live and die alone. In such a world, society would completely restructure itself to maximize eye contact. We might build massive conveyor belts to move lines of people past each other. More realistically, we'd use technology. Imagine a global version of chat roulette, where people spend hours every day staring into strangers' eyes, hoping for that one spark of recognition. But even then, it would take decades to match everyone up, and few could afford to devote their lives to the search. Jobs like cashier or Times Square police officer would become high-status careers, prized for their eye contact potential. People would flock to cities with desperate, frantic energy. And in a world with so much pressure to find the one, many people would simply fake it. They'd find another lonely person, stage a public soulmate encounter, and spend their lives pretending to be happy, hiding their deep loneliness from everyone they know. A world of random soulmates wouldn't be romantic. It would be tragic. It would be one of the loneliest worlds imaginable. Let's hope that's not the one we live in. The questions we've explored so far have been about physics, biology, and society. But Munroe's NASA background often leads him to questions about space. And his answers reveal just how counterintuitive space travel really is. Several readers asked variations of questions like, couldn't a spacecraft slow down to a few miles per hour on re-entry to avoid needing a heat shield? Or, couldn't we just lift a rocket high into the atmosphere to make it easier to reach escape velocity? The answer to all these questions hinges on one profound idea. The reason it's hard to get to orbit isn't that space is high up. It's hard because you have to go so fast. Space is only about 100 kilometers away. That's not far at all. For many people on Earth, space is closer than the nearest ocean. Getting to space is relatively easy. You could launch a person there with a rocket the size of a telephone pole. The challenge isn't getting there, it's staying there. When you're in low Earth orbit, like the astronauts on the International Space Station, you're still very much in Earth's grip. Gravity at that altitude is about 90% as strong as on the surface. Astronauts float not because there's no gravity, but because they're in continuous free fall. They're constantly falling around the Earth. To avoid falling back into the atmosphere, you have to be moving sideways at an incredible speed, about 8 kilometers per second. That's roughly 17,500 miles per hour. Think about that for a moment. 8 kilometers per second. Fast enough to circle the entire world in about 90 minutes. If you fired a rifle bullet from one end of a football field, the International Space Station would cross the entire length of that field before the bullet traveled even 10 yards. The vast majority of a rocket's energy isn't used going up, it's used going sideways, gaining that immense orbital speed. And this is why you can't just slow down when re-entering the atmosphere. You have to get rid of all that sideways velocity. Doing that with rockets would require carrying an absurd amount of fuel, so much that you'd never have gotten into orbit in the first place. This is the tyranny of the rocket equation. Fuel makes you heavier, and the heavier you are, the more fuel you need to lift yourself. It's exponential. That's why every spacecraft re-entering an atmosphere uses a heat shield. Slamming into the air is the only practical way to bleed off that incredible speed. The fiery re-entry isn't a problem to avoid. It is the solution. It's converting that mind-boggling kinetic energy into heat, slowing the spacecraft enough to land safely. It's not about the height. It's all about the speed. Speaking of space, one of the most poignant questions in the book comes from reader Brian McCarter, who asked, "What is the farthest one human being has ever been from every other living person, and were they lonely?" The most likely candidates are the 6 command module pilots from the Apollo missions that landed on the Moon. While 2 crewmates descended to the lunar surface, 1 astronaut remained alone, orbiting the Moon in the command module. At the highest point in their orbit, on the far side of the Moon, they were about 3,585 kilometers, nearly 200 miles away from their fellow astronauts on the surface. And because the Moon itself blocked all radio signals, they were completely cut off from the other 3 billion humans back on Earth. In those moments, they were the most isolated humans in all of history. Could anyone else have come close? Maybe. Perhaps a lone Polynesian sailor, blown off course centuries ago. drifted to a similar distance from any other person. Or an Antarctic explorer, the last survivor of a doomed expedition. We'll probably never know for sure. For now, the title belongs to those 6 Apollo astronauts. Which brings us to the deeper question, were they lonely? After his mission, Apollo 11's command module pilot Michael Collins wrote about his experience. He said that far from feeling lonely or abandoned, he felt very much part of what was happening. He described a feeling of solitude, yes, but also connection. He wrote, "I am alone now, truly alone and absolutely isolated from any known life. I am it." Al Worden, pilot for Apollo 15, had an even more surprising take. He said, "I was alone, but I was not lonely. I thoroughly enjoyed it. I didn't have to talk to Dave and Jim anymore. On the backside of the moon, I didn't even have to talk to Houston, and that was the best part of the flight. It's beautiful, isn't it?" The loneliest human in history wasn't suffering. He was just a guy who was happy to finally have a few moments of peace and quiet. The questions in this book often lead us down these strange, wonderful, and sometimes deeply human paths. They start with simple curiosity and end with a new way of seeing the world. Let's explore one more, a question that sounds almost like a riddle, from reader Vittorio Iacovella. What if a glass of water was, all of a sudden, literally half empty? He doesn't mean half full of air. He means half full of a perfect vacuum, nothing. What happens next depends entirely on which half is empty. Let's imagine 2 scenarios. First, the top half of the glass is vacuum, with water sitting peacefully at the bottom. Second, the bottom half is vacuum, with water mysteriously suspended above it. In the first scenario, with vacuum on top, the result is surprisingly quick and violent, but contained. The surrounding air, at 14.7 pounds per square inch, instantly rushes in to fill the void. After a few hundred microseconds, the air slams into the water's surface, creating a pressure wave and a loud bang as the shock wave spreads out. The glass shudders but survives. The second scenario is far more dramatic. If the vacuum is at the bottom, the water is held up only by its own inertia for a split second. Air pressure from above pushes down on the water. Air pressure from below pushes up on the glass. With nothing between them, the water and glass begin accelerating toward each other. In less than 10 milliseconds, they're flying toward each other at several meters per second. Without an air cushion between them, the water smacks into the bottom of the glass like a liquid hammer. Because water is nearly incompressible, the impact delivers a single, sharp, immense shock. The glass doesn't just crack, it shatters. This is called a water hammer effect. It's the same principle behind the party trick of smacking the top of a glass bottle to blow out the bottom. The sudden motion creates a tiny vacuum bubble inside, and when that bubble collapses, the shock breaks the glass. In our scenario, the bottom of the glass gets obliterated, but the story isn't over. The upward force on the now detached upper portion sends it flying into the air. It rises, bangs against the ceiling, breaks into more fragments, and rains back down on the table. And so we have the final answer to the age-old question. If the optimist says the glass is half full, and the pessimist says it's half empty, the physicist ducks. As we reach the end of our journey through What If, it's easy to feel a bit dizzy from all the delightful chaos. We've watched planets stop spinning, baseballs trigger nuclear explosions, and oceans drained to reveal new worlds. But beneath all the humor and wonderfully absurd scenarios, there's something deeper going on in Randall Munroe's work. This book is a love letter to curiosity. It's a powerful reminder that the questions we're taught to dismiss as silly, childish, or impractical are sometimes the most valuable ones we can ask. The adult world focuses so much on how and what is. We learn the rules, memorize the facts, understand the way things are. But somewhere along the way, we forget the exhilarating power of asking what if. Munroe shows us that this simple question is the starting point for all real exploration. It's the engine of science, the spark of innovation, the soul of creativity. When you ask, what if a baseball went at 90% the speed of light, you're not just being silly. You're creating a playground for the laws of physics, a space where you can see how relativity, thermodynamics, and nuclear fusion interact in ways no textbook could ever show you. You learn not by memorizing, but by playing. What's truly remarkable is how Munroe treats every question with respect. No matter how absurd the premise, the science is always real. He pulls from research papers on ICBM nose cones to calculate the cooking of a falling steak, and uses data on geothermal plant maintenance to estimate the timeline of our world without us. This commitment to seriousness in the face of absurdity is what makes the book brilliant. It teaches us that any question, no matter how strange, can become a gateway to genuine understanding if we're willing to follow it with rigor and an open mind. So what can we take away from this? How can we apply the spirit of what if to our own lives? First, start asking more stupid questions. Next time a strange thought pops into your head, don't dismiss it. Follow it. See where it leads. What if you could jump to the moon? What if trees could walk? What if we lived on a planet with 2 suns? You don't need to be a NASA roboticist to explore these ideas. You just need a little curiosity and a willingness to look up the answers. The journey of finding out is often more rewarding than the answer itself. Second, embrace thinking from first principles. When faced with a complex problem, don't just accept conventional wisdom. Break it down. Ask fundamental questions. Munroe doesn't just say it's impossible. He shows why by starting with basic laws of physics and building the scenario from the ground up. This way of thinking is a superpower. It lets you see the world with fresh eyes and find solutions others might miss. Ultimately, this book is a love letter to human imagination and its partnership with logic and reason. It shows that science isn't a dry collection of facts, but a thrilling, dynamic, and often hilarious adventure. It's a tool for making sense of the universe and for dreaming up new ones. That was our exploration of What If by Randall Munroe. We've touched on some mind-bending ideas today, but here's the truth. A summary can only take you so far. The real magic happens when you read it yourself. It's in the delightful stick figure illustrations, the witty footnotes, the sheer joy of discovery on every page. This summary is a map, but the treasure is in the book itself. If anything we've talked about today sparked your curiosity or made you smile, grab a copy. Reading it isn't just learning. It's an experience that can genuinely rekindle your sense of wonder about the world. Also, if you found this journey valuable, please consider liking this video and subscribing to our channel. It helps us continue exploring incredible books and sharing their wisdom with the world. Let's keep asking questions and keep growing together.